Welcome back to Calculus. Today we are looking at section 7.2, exponential change and separable differential equations. So we're going to start with some exponential change and we'll move into the separable differential equations, which just sounds super fun. So let's say that we're given that our rate of change for something is a linear function, ky, with y equal to y sub 0 and t is equal to 0. All right, so we have a rate of change here, or at least we have a function for a rate of change. And yes, I need to plug in my computer, so give me just a second. All right, so we're back. Had to move the computer over just a little bit. It's okay, we can still see my board. Where was it? All right. Oh yeah, we were working our way through, or getting ready for this. So taking that into account, we have this rate of change is a linear function, ky. We can think of that then as 1 over y dy dt is equal to k. So I just multiplied both sides by 1 over y to move that y over. Then, if we integrate both sides, the right side is really straightforward. It just becomes kt plus c. The left side, now 1 over y times dy dt, if you remember back from section 7.1, we had an antiderivative for f prime of x over f of x. And that's what this is. Okay, I could write this on the top, the dy dt, and it would look more like what we had there, but that's exactly what this is. So if we integrate this piece with respect to t, we just get the natural log of the absolute value of y. So then doing a little bit of work to get y by itself, I put both sides, I switched to exponential form to get rid of the logarithm, so we have the absolute value of y is equal to e to the kt plus c. And then I can rewrite my exponent here because we have the addition as e to the c plus e to the kt. And then to get rid of the absolute value, we just throw a plus or minus in front. But now we have this plus or minus e to the c. That's just an initial amount of something. So if we're talking about exponential functions, or exponential growth, exponential change, which is what we're looking at here, we have this wonderful exponential function, y is equal to a times e to the kt, and that's where it comes from. So if the rate of change of your whatever your system is a linear function, you end up with an exponential function as to describe what's happening. All right, so let me get this board cleared and we'll move on and do some more stuff. All right, so continuing on, let's look at what separable differential functions are. So let's say we have dy dx and it's equal to f of x comma y. This is a function of two variables, okay? F is a function of both x and y. It's separable if it can be written as dy dx is equal to g of x times h of y. Basically, it's a separable function if you can write two functions, one for x, one for y, and the function you started with is just the two of them multiplied together. So for example, let's solve this separable differential equation. We have dy dx is equal to 1 plus y times e to the x. So in this case, here's my g of x and my h of y. Right. There we go. Right? The x and y, basically x and y are completely separate from each other with multiplication in between. So to solve this, what I want to move all the y's to one side and all the x's to the other. So I divide both sides by 1 over y and multiply both sides by dx. So I bring the 1 plus y to the bottom of this fraction, and the dx multiplies and moves over. Well, what that does for us then is it allows us to now integrate both sides. Because now we just have one variable on the inside of both sides. And so we can get rid of our dy and our dx, and we can end up back with an original equation. In this case, the left-hand side is the natural log of 1 plus y. Notice here that using the chain rule, the derivative on the inside is just 1. So that's why there's nothing else over here. And the integral of e to the x is e to the x. We only need one constant. We're integrating both sides. You could put a c here and a c there. But guess what? Then you can move it over and just have another arbitrary constant which is what we did. We just have one constant here, that's all we need. And so here's the original equation that would have that differential. All right, let's take a look at another one. Okay, one more separable differential equation. dy dx is equal to x squared, square root of y. Again, I'm going to move the y's from one side, x's to the other. So I divide both sides by the square root of y, multiply by that dx, giving me dy over the square root of y is equal to x squared dx. Just like before, I'm going to integrate both sides. The right-hand side is the easier integration here. If you integrate x squared, it goes up to x cubed, multiply by its reciprocal, there's our 1/3 x cubed plus c. The left-hand side is a little trickier, and I didn't write it all out, but basically this is y to the negative half power. This is not a natural log. We don't need it because we have a power here. We can do this as a polynomial. So y to the negative half, if you add 1, you get y to the half. That's my square root. And you multiply by its reciprocal, there's our 2. Feel free to think it through and try it out for yourself. So the last thing in this section, and I do still have an example, but I couldn't fit it onto my board space, is unlimited population growth. And it has a lot of assumptions built in. So feel free to take a peek at your book and see some of those assumptions. I believe it's on page 405 in your book. But let's say that the change in population, so if y is our population, the change in population with respect to time is going to be equal to the birth rate minus the death rate. Right? That makes sense. If your birth rate is higher than your death rate, you have a positive change in population. And if your death rate is higher, you get a negative change in population. You have a shrinking population. And that's going to be equal to some constant times y. All right, so we know, because we just did this, that if we have a dy dt equal to a constant times y, that we can get it as y is equal to, I'm using y sub 0 here instead of the a that we saw before, but it means the same thing. It's our initial condition times e to the kt. And so we're going to use this, and we're going to use it to do some population problems. So give me just a second, and I'll put one on the board. All right, so here's our exponential problem. The number of people cured of a disease is proportional to the number infected. Suppose that in a year's time, a cure reduces the number of cases by 20%. There are 10,000 cases today. When will there be only 1,000? All right. So we're going to use our exponential function. No calculus required here. The calculus is all underpinning what we're doing. That's wonderful. That's just why this exponential stuff works. So I'm putting in 10,000 for the initial number, and since we have a reduction of 20%, I'm going to put 8,000 over here for y. Because here's the thing, I don't know k yet, so I can't go directly to figure out when we get to 1,000. All right, so I plug in 8,000, and I'm going to plug in 1 for t as well, because we get that 20% reduction in 1 year. So if I do that, plug in 1 for t, if I divide both sides by 10,000, I get 0.8. So then switching that to a logarithm, we get the natural log of 0.8 is just equal to k, because that's 1, and we end up with k being negative 0.223, which now then gives us our full exponential model. We have y is equal to 10,000 e to that negative 2.223, or I'm sorry, negative 0.223 t. And so now we can plug in the 1,000. We want to know when do we get there. So these exponential problems usually end up being 2 steps. One step to find your constant here, and the other to actually find what you're looking for. So again, I divided by 10,000, I got 0.1. I changed to a logarithm, so the natural log of 0.1 is equal to that negative 0.223t. And if you divide, you get 10.3. So it's going to take 10.3 years to knock these cases down to 1,000. I don't know, personally it doesn't seem like a great cure, but I suppose that's a lot better than 10,000. So, all right, there you go. Have a great day.